Well, so our next unit is on interferometers, and before beginning with that, I thought of making a quick overview of this unit, which is on interference. And most of the contents which have been put in this presentation are taken from this book on Introduction to Optics. And I really thank the contributors for their nice work. So one topic which we had done already, I hope you have already been through this, but here I want to do a quick overview of this Lloyd's mirror. And in this experiment, we actually obtain interference pattern with the help of a very simple arrangement. And in that simple arrangement, the we simply use a mirror which is placed in a direction horizontal, and then we actually put a source of light near to the mirror, and the interference is produced because of this superposition of two light radiations. I mean, two light beams, we should rather say. One which is reaching to the screen directly from the source, say suppose this light beam coming this way, and of course this is also directly coming this way and then getting reflected, and then a ray which is just close to this, which doesn't at all suffers reflection, comes to the screen. So the reflected beam and direct beam from the source both leads to the uh, superposition, both superpose with each other, which finally lead to the formation of interference pattern on the screen. The idea is very simple. uh, Now let us try to obtain quantitatively the expression for condition for this maxima and minima to be produced on the screen as a result of this arrangement called Lloyd's mirror. So to do that, let us first uh, draw a line in the plane which is actually containing our mirror. So this is a mirror which is actually perpendicular to this the plane in which this whole diagram has been drawn. So the mirror is just perpendicular to that, and then we are drawing a line which is uh, just like a perpendicular on to this line, or we can say that if we draw a perpendicular from source on the plane containing mirror, then that is this line. And now we have to actually obtain the total path difference. If we have to see, okay, what will be on the screen, will it be a maximum or a minimum? To see that, what we do is we take a reference point, say P, on the screen, and then the light coming from, say, this source S, like this, and the one which probably would have come here and then got reflected may also be will also be reaching here. So now whether these two will cause maxima or minima, that depends upon what is the path difference between the two, and that's what we need to evaluate. So to find out path difference, we first of all note in this figure that the geometric path difference between these two will be S dash P minus SP. So this is S dash P, this is your total length from this point to this point, and SP is the length from this point to this point. So this is geometrical path difference. And I hope you know what is the difference between geometrical and optical path difference. There we have to consider the refractive index. Fine. So now we have to find out this S dash P minus SP. To do this, let us draw a perpendicular here from S on to A. It's onto this line, say S dash P. Let us draw a perpendicular SA, and at the same time, let us assume that the angle which this line, say S dash P, makes with the horizontal line is theta. So if this angle is theta, the angle in this triangle, say S dash, the angle S dash SA will also be theta. Why it will be theta? Because we know that the angle between any two lines and their perpendiculars are same, correct? So this line and this line has an angle of theta with each other, and the perpendicular to this line is this one, correct? And perpendicular to this line is this one. So these two perpendiculars will also make an angle theta with each other. So this angle is theta. Well, if this angle is theta, then we have a right angle triangle here, S dash AS. And in that right angle triangle, if I write down sine of theta, what will be sine of theta? Sine of theta will be equal to perpendicular over hypotenuse, correct? And the perpendicular is nothing but S dash A, and this S dash A is nothing but the path difference, because beyond this point these two have same length, correct? Therefore what we can say is the path difference is this one, S dash A. Let us say that is delta. So basically delta will be nothing but A sine of theta. You can find it out. So in terms of this A, the you can say separation between say two sources. So this source is the real source, this is the imaginary source, which is just a reflection, which is just image of this source because of reflection in the mirror. So S dash. So this is the separation. So now what we have to write down is the optical path difference. This is the geometric path difference, correct? The optical path difference will be delta, the geometric path difference, this much, plus a sudden path difference faced at this point because of reflection. Now I hope you have understood it well, that whenever light suffers reflection at interface of two media, such that the lower medium is having higher refractive index in comparison to the one which is here above, there happens a sudden phase change of pi, and that phase change of pi because of reflection leads to a path difference of lambda by 2, because phase change of 2 pi is equal to path difference of lambda, and phase change of pi will be nothing but equal to path difference of lambda by 2. So here is the total optical path difference, and this total optical path difference for constructive interference has to be equal to m lambda. In case at this point we have a maxima, that will happen only when this path difference is nothing but m lambda, and then we can substitute the value here. Very simple. We will get this one, and now to get the position of this maxima and minima on screen in terms of the length from this point, say just let us say this is 0 reference on y-axis, then we want to obtain, okay, where will be the maxima or minima on the screen. So right now we are focusing on maxima, so let us obtain the condition for that. So in that case we can assume, okay, let us not put the source very far away from the mirror, keep it close to the mirror, so that in this distance we can say is not very large, so that I can even assume this triangle, say this one, let's say midpoint, I don't know, I have not named it, let me for time being assume it to be say Q or B, what, let us say B. Then we can say that, okay, in say triangle this one, this triangle, and connecting at point P, right? So it is something like, okay, this line connecting here, so this angle is going to be slightly lesser than theta, but we are saying, okay, this distance is small, so this angle is also very close to theta. Then to obtain sine of theta we can assume this triangle actually, and then write down the expression for sine of theta in this triangle, and that will be nothing but the perpendicular. So let us say this is y as such divided by hypotenuse. So hypotenuse is this one, right? But now there is another approximation which we are making, that okay, let us assume the screen is placed far away from this mirror, or even if not so, let us say the size of the screen is not very big. So we are assuming screen is very less, such that the hypotenuse can be taken to be almost equal to the base. If the angle is small, means theta is small. And what is the circumstances? What are the circumstances which can lead to theta being small? Theta being small is, if you reduce the size of the screen, obviously the point P will lie somewhere on the screen, and then theta is going to be small. So size of the screen is very less, it's not very big screen. In that case, we can say, okay, the hypotenuse is close, almost same, or very near to the value of the separation of our screen from these two sources, or the line containing these two sources. This is not two real sources, this is real source, this is image of the same source. So in that case, we can write down sine of theta is nothing but y perpendicular upon hypotenuse, which is close to s. That is why this is almost equal to sine here. So sine of theta we can write down with this. This is the approximation which we have been using most of the times. Even when we had done that Young's double slit method, we had used that approximation. Now we put the value of sine of theta here, and so we are saying we are small index ym. Now let me not put y as a random value, but okay, let us find out. Let us put it to be referring to a particular mth maxima on the screen. So this is ym, so this is a ym by s plus lambda by 2 is equal to this. So what will be the condition for maxima on the screen? That will be equal to this one. So I can take lambda by 2 there, that side, so this will be m minus half lambda s by a. So that is the condition for maxima on the screen. I would like to bring your attention to the condition for maxima given in the book. This is not the correct expression, because what they have missed is the what you call sudden path change. So if, because during reflection, ray suffers a sudden phase change of pi by 2, so that has not been taken care here. So this as such is wrong. So this is the correct expression. Yeah, this you can say is the expression for dark fringe, or minimum intensity on the screen. You can say there we won't be we won't be taking sudden path change has to be taken, but then that has to be equal to half integral multiple of wavelength. In that case, we will arrive at this expression. That's okay. Fine. That's a quick overview of what is Lloyd's mirror. Now there is a question which you can ask yourself. What happens when the screen just touches the mirror? Suppose we bring in this screen close and to this point, say m dash. What do you think you will, or you should observe at the point which is just close to this point, means at the middle of the screen? What will you obtain? Will that be maxima or minima? Pause this video, try to think, and then come up with your answer. Okay, so that of course is going to be a minima here. Why? So one wave coming from here, let us say very close to this, but which doesn't suffer reflection here, and other wave which just reaches here on the edge of the mirror and just gets reflected, and two superposed with each other just very close to this is the screen. So now one wave has no sudden phase change because it has not been reflected. Other one has a sudden phase change of pi by 2, means path difference of lambda by 2. So what will happen? The two, when they will superpose, will lead to cancellation of their amplitude, and overall what you will be obtaining on the screen will be a minima. Fine. Okay, now let's talk about another arrangement for seeing interference pattern, and that is Fresnel mirror. So Fresnel mirror is also a very simple arrangement. Actually, it is arrangement of two mirrors, say M1 and M2, which are kept at a very small angle with respect to each other, say theta. So in Lloyd mirror we have one single mirror, and here we have two mirrors which are inclined at some small angle theta with respect to each other. So this is a first mirror. Just note that highlight, right? And this is first mirror. and this one is the second mirror M2, and both are at some angle theta. The condition is very simple. If you see here, to obtain to obtain the condition for interference, so the situation is quite simple. Okay, this is source of light. From here, what happens? The light reflects, falls on this mirror and suffers a reflection. That's 1. Why we are saying 1? Suppose this is coming from a image of this source, which is formed because of the reflection of rays in the mirror M1. So we are saying 1. Similarly, other ray coming from this source, and the ray gets reflected just from the point which is on the edge of the first mirror, and just on the junction of the two mirrors, but reflection is occurring from the edge of the first mirror M1. And that ray, of course, you should try to draw a perpendicular on this one. So one mirror is suppose in horizontal plane or in horizontal direction. In that case, the perpendicular is going to be like this. So this will be the reflected ray coming from the reflection of this edge of this mirror M1. Angle of incidence has to be angle of reflection following that. And you will see if you draw this back, it should meet here at S1. Correct? That's, of course, you take any ray reflecting from this mirror, getting here, so that should actually connect at S1. That's why we should see its image in the mirror. Correct? Now, and there is another situation, the ray which is going like this and very near to edge, but now reflects from the edge of the mirror M2. Now here the perpendicular is slightly at some angle, and the both perpendiculars should make an angle theta with each other, isn't it? Because the angle between two lines and their perpendiculars are same idea here. So one perpendicular like this, other perpendicular slightly like this, both at say angle of theta. I'll be showing it on the next slide. So then the ray which will be reflected from this one, the just edge of this one will be this one, say 2. So that is what is marking the ray 2. And if you reproduce it back, it should come somewhat here to S2. And there is another ray which is falling from here onto this mirror. If you again produce it back, it should come here to S2. So that is how, okay, we have two sources now, S1 and S2, which are mirror images of this actual source, and now the interference is produced because of these two images of this same source, and the direct light doesn't contribute anything to the interference, so that would be going like this, no problem. Screen size is small, so we are saying okay, the interference is coming because of the superposition of the rays coming from source 1 and source 2, which are here S1 and S2. Correct? Now to obtain the condition for maximum, what we need to know? We need to know what is the path difference suffered by the two. So even for that, we need to first consider this triangle, say S1PO. So this is S1. Let me name this point as P here, which is okay. Before we do that, let me assume this point as a center point and draw a sphere actually around this. Rather, circle will be sufficient. So a circle of a radius, say D. What I'm doing is I'm drawing a circle of radius D from this point. Then you should see that these images of this source S1 and S2 would be formed on the circumference of this circle. Why on circumference of this circle? So okay, if this distance is D, this image will also be formed at distance D. This image will also be formed at distance D, S2. Why so? Okay, let us take a simple say logic for this. The light which is traveling from here should reach or should travel a distance D in same time to reach here as if it would take to reach from here to here and here to here, right? So if the distances are same, of course time is going to be the same. So I mean, if we say okay, this ray is coming from this source that would mean the distance of this point from this source should be same as the distance of this point from this source, and the same logic applies to this one. So that is why actually images will be on a distance d from this point, say O, or because we are completing a circle, so this is like a circle, and all the points, this point has a fixed distance d from uh, the circumference of the circle, any point on circumference of this circle. Now now let us consider on, or let us focus on triangle S1PO. S1PO. So this we can assume to be almost like a perpendicular or a right angle triangle. This distance is very small, so if I draw a line here, it would be almost like a perpendicular and having a 90-degree angle. So now we will say, okay, what will be this angle? S1OP. What we are seeing? S1OP, that will be equal to theta. But before that, we need to know why is this angle S1O S2 is 2 theta, right? So again, let us try to recall what was theta. Theta was the angle between these two mirrors, M1 and M2, right? Now what we are saying is this angle has to be 2 theta, S1O S2. So this can be first of all, now what we want to prove or check is why is this angle 2 theta. So before proceeding further, let us first try to see why is that angle equal to 2 theta. So I'm just skipping it, I'll come back to this. Let's come here on to the question that why that angle is 2 theta. So here's the situation. We have, say, mirror M1, we have kept a source here, correct? Let us assume and then we have another mirror, say M2, and these two are at some angle, say theta. Now this is a source, so if I take a ray of light coming from source S1 and just hitting onto the edge of mirror M1, and the edge is close to the point where the two mirrors join to each other. So what will happen? So if this is the perpendicular to this mirror M1, this ray should be reflected according to laws of reflection, and that is what has been marked as 1 in the previous diagram. So this ray should be reflected like this. So if this angle is, say, angle of incidence, let me say if this angle is x, then what should this angle be? This angle should be x itself. This is just simply law of reflection. Well, and if I produce this ray back, this would be going back to somewhere onto the source, say S1, or image of this source due to reflection in mirror M1. I hope you're getting it fine. Now let us, so we know this angle is theta, okay, fine. What will be this angle in that case? Because this is perpendicular, fine. This angle is theta. This total angle is 90 degree. So what will be this angle? This will be 90 degree minus theta. Fine. Keep it with you. Come to the next thing. Now again onto the same edge, we are now drawing perpendicular to mirror M2. Now angle between two lines and their perpendiculars are same. So means this angle should also be theta. If this is theta, then this also has to be theta. Now let us see the reflection of this same ray. I mean, now this is suppose falling on mirror M2. Then angle of incidence is x minus theta. I hope you could imagine, you could see it here. If this total angle was x, so what will be this angle? This angle will be x minus theta. So how would it be reflected? At an angle x minus theta. So with this perpendicular, the reflected ray should make the same angle as x minus theta. So I'm drawing that with a green color, say. So what will be this angle is nothing but x minus theta. Very good. Now we are in a very good position to see what would be the angle between these two rays. So before that, let us reproduce this line back, and this would be going back to image of the source S2, which we were marking S2 in the previous figure. Now what we actually have to find out is this angle, the angle between these two. So what we have to prove that angle S1 O S2 was nothing but 2 theta, right? So we have to now find out this angle, and if it comes out to be 2 theta, our job is done. So let us now try to find out what will be this angle. Fine, let's assume this angle is P. Now if you come here now, then what will be this angle? This angle is going to be 2 theta, x minus 2 theta. Why? Because this total angle is x minus theta. Out of it, if I subtract this theta again, what will be this angle? This angle will be x minus 2 theta. Correct? Now our task is very much simplified. So what will be, let us focus on this quadrant actually. So what will be the situation? It's like x minus 2 theta plus p plus 90 degree minus theta plus 90 degree minus x minus theta, which we already have obtained earlier, plus theta should be what? This total angle is nothing but 90 degrees. So we are summing all those angles, and we know that is nothing but 90 degree because this is perpendicular to this. So what is that? X minus 2 theta, this one, plus p plus 90 minus x minus theta, so this one actually, plus theta, this one, equals 90 degree. Correct? So here this 90 cross cancels on both sides. This theta cancels with this, x cancels with this. What we find out finally is p is equal to 2 theta. So this angle P is nothing but 2 theta, and these are two opposite angles. So angle between S1 O S2 will be 2 theta, and that's what we have. So that is your S1 S2, correct? So S1 O S2 will be nothing but 2 theta. Well, so that's what we have already done in the previous slide. So let us go back now. So I will be using that here. Okay, so this is our angle S1 O S2 is 2 theta. So now now let us focus on this triangle, say S1O S1PO S1PO. This angle will be theta. So this is because this is a bisector of the these two. So in that case, if I write down in this triangle S1PO, sine of theta, that will be equal to, say, perpendicular, which is nothing but S1P divided by hypotenuse S1O, and S1O is nothing but D. Remember that argument. If this is D, this is also D, this is also D, so this is D. And what is S1P? This total distance between S1 S2 is, say, A. I hope you remember the notations which we were using. So in Young's double slit method, we were using the separation between two sources as A. So what will be this? S1P, this will be A by 2. So that's what we have done here. So A by 2 divided by D is equal to sine theta. And now let us assume that theta is not very big. In that case, we can say, okay, theta is close to say 0. In that case, sine theta is almost equal to theta, and our condition is simplified. So theta will be nothing but A by 2 divided by D, and from here we can do further simplification and prove that A, the separation between these two sources causing interference, will be 2 theta into D. What is D? Distance of this source, real source, from the edge where the two mirrors are joined to each other. Fine. Now our task is very simplified. So now it is something similar to Young's double slit method. So you have two sources of light. These are coherent, of course, because they are derived from the same one. These are two sources, and what is the distance between these two sources and the screen? Suppose the point O is at a distance D from the screen, capital D. So the total distance between these two sources and the screen will be small d plus capital D, because this is from here to O is small d and from here to here is capital D. So total separation between the sources and screen is capital D plus small d, and we have already done this here. So small a separation between two sources is this. So what will be the condition for maxima? Ym, this is again coming from the Young's double slit method. This is m into lambda into capital D, that was in their case, I mean distance between the sources and the screen. Here it is written with the help of small s, divided by small d, the separation between two sources, and here it is a and we know what is a, so we just substituted the value. So this is the condition for maxima in the Fresnel mirror. Now you should ask one question here: why didn't we incorporate that sudden phase change of pi by 2 here? Because we are seeing the rays are seeing reflection from mirrors. So basically this is because the sudden phase change is happening for both the rays which are producing interference, or both the beams we should say. So one beam coming from this mirror M1, that also faces a phase change of pi by 2, and the second beam which is coming from mirror M2, that is also facing a phase change of pi by 2. So both balance each other. That is why we don't have to consider, or we don't need to consider that. So if one is suffering, other is also suffering the same. So these two will cancel with each other, and hence the final condition for maxima on the screen will be this one, Ym is equal to this one. Well, so that's about Fresnel mirror. I hope yeah, that's fine. You are comfortable with this. Now this part we have already done, so I am skipping. Now yeah, come to next arrangement, and this arrangement is on Fresnel biprism. So this is also an arrangement in which we can actually produce interference pattern, and basically Fresnel biprism is nothing but a prism which is made up by joining two prisms. That is why it is called biprism. So it is and this angle actually is very small, alpha. It's very close to 180 degrees. Sorry, this angle is close to 0 degrees, and this angle is close to 180 degrees. So that is why. So this is, there is one prism like this one, and there is another prism like this downwards, correct? So this is a biprism. It's not like, okay, we take two two separate prisms and then try to connect them with the help of some glue. No, it's not like this. We actually produce this from a single piece of glass and give it this specific shape to obtain Fresnel biprism. Okay, the geometry is quite clear. So what you have is you keep a source here. So this source, so this, suppose there are two rays coming from say one is coming like this. This is like a point source, or you may have a slit here. So one ray coming almost at 90 degree to this surface. So this is close to normal incident. So it will go as such without bending to any direction. And here when it goes out, so you can see this is like, okay, perpendicular to this surface, so it will bend away from the normal. So this is air here, other everywhere else is air. So this is, say, made up of some material, say glass or flint, whatever, different type of glass. So it will go like this, correct? Similarly, a ray which is coming very near to the edge of this prism, this will be deviated minimal, very less. I mean, okay, I mean, from here it will be deviated like this. It won't be deviated very less, but it will be coming symmetric to this one, because this the size is very less, so it would be going as if it is going like symmetric way to this one. Fine. And the condition is condition for going symmetric happens when the deviation is minimum. So that is why I hope you have done it in the elementary classes, where you had seen that, okay, what is the condition for minimum deviation? That when the incident and emergent rays are symmetric to the base. So that's the same thing. So if we take this as angle of prism, so this is almost symmetric, and that is what would refer to the angle of minimum deviation for this particular ray. Now we have to see, okay, how the two will produce interference. So this ray has some different path. This ray has a different path. So all these rays coming from different parts of this biprism, from this end and this end, would be having different path difference, and then depending upon how they reach on the screen and what is the overall path difference on the point on the screen, we can see constructive or destructive interference, and hence the interference pattern can be observed on the screen because of this arrangement of what we call the Fresnel biprism. To see a theoretical derivation of how we can obtain the condition for this one, this is the condition for maximum obtaining maxima on the screen. How we arrive at this, we are just going to see it very quickly here. So we can, I hope you have done this in your earlier classes, that refractive index is at angle of minimum deviation, the refractive index is equal to sine of alpha plus delta m by 2 divided by sine of alpha by 2. So this is alpha here, right? Angle of prism, we are taking this one as the angle, so because this is the condition for minimum deviation, so this is the angle of minimum deviation delta m. So that's all what we have put here. Now since this is alpha and delta m are very small, because this also won't be deviated very much, it is just appearing here that it is deviated a lot, because we have taken biprism having this angle to be very large. Practically this angle is very small, so this is deviated very less from its original path. So that's an important thing here. Fine. So that is because of what we can take this angle to be almost equal to this only. Sine of theta is almost equal to theta, for theta being small. So we can say, okay, refractive index is just this one in that case, for special arrangement made in the Fresnel biprism. And by simplifying this, so we can just do rearrangement of things. I can take this to that way, 2 cancels with this 2, and then rearranging the things we can find out delta m is equal to alpha into n minus 1, where n is the refractive index of the material of the prism. Now to find out this condition for maxima, we consider this triangle, this one, which just is going to highlight here. Yeah, let's consider this triangle S1P, say point here, and we can assume this small portion of this or the edge of our biprism to be behaving almost similar to that of a convex lens. This is an approximation now we are using. And what happens in a convex lens, if we have a light coming from a point source, that will be going like this, and this ray will go parallel to the axis through the center of the lens. So if this is going parallel to the center of, if this is going parallel to this axis, in that case, this angle is almost 90 degree. And if this is delta m, the angle of minimum deviation, so this will be opposite angle, and of course is also delta m. Now in this triangle SS1P, rather right angled triangle SS1P, we can write down an expression for tangent of delta m. So tangent of delta m is equal to nothing but perpendicular upon base, right? So what is perpendicular is nothing but a by 2, and base is nothing but this d, the separation of the biprism from the source, or perpendicular distance of the source from the biprism. And we know that whenever this delta m is very small, we can write down tangent delta m is close to delta m itself. It is same approximation which we use for sine theta. Sine theta is almost equal to theta. So tangent theta is what? Sine theta over cos theta, and as theta approaches 0, cos theta approaches 1, and sine theta approaches theta. So that's the same thing. That is delta m. what we can write down. So now if we use this equation, simplify it little, we will be finding A is equal to 2 delta m into d. So basically what we need is the separation between the two sources, say two virtual sources which are causing interference. And then once we know this, this is a by 2, so total distance between s1 and s2 will be a. So in that case a is 2 delta m into d, and we know what is delta m, we have just obtained here. So in that case a will be equal to 2 into d, so this 2d into delta m, so which is nothing but alpha into n minus 1, n is the refractive index of the material of the biprism. And once we know this, now we can apply the condition from this Young's double slit method. So the condition for maxima will be equal to m lambda, m is an integer, m lambda into cap d, the distance between the two sources and the screen. So the total distance between two sources and the screen is small d plus small s, so that's what we have written here, divided by a, small a, the distance between the two sources. And what is that distance between two sources? A, this is 2 into delta m into d, so we have substituted value of delta m here. So this is the condition for maxima in Fresnel biprism. So mth order maxima on the screen can be obtained by using this condition. Well, next, what is very interesting was this interference in the thin films. I'm sure you have gone through that article which was discussed on a video lecture that I had shared with you on NPTEL. Now, okay, what was the condition? So the condition remains same. The path difference should be equal to integral multiple of the wavelength of the light, and here the path difference delta, geometrical path difference actually, no, this is optical path difference, okay, because we are taking care of this refractive index as well. So total the optical path difference, which we would say AD, between the ray which is coming from this one. So what happens in thin films is, if you incident a ray here, it will be partially reflected, partially transmitted. So this transmitted ray, according to Snell's law, this is angle of incidence, angle of refraction, theta t, we are saying angle of refraction. Okay, so that's what is theta t here. Then this will go here, travel in the medium. So suppose refractive index of the medium is nt, t we are saying for film. Okay, NF actually we are saying refractive index of the film, and naught is the refractive index of the upper this surface from where, or this medium from where the ray is coming. Usually it is air, but it can be different one as well. So fine, it is reaching, it suffers a reflection here, a part of it may even be transmitted, so we are not bothering about that right now. So it will be reflected back here again, a part of it will be transmitted, part of it may even be reflected. So if t is the thickness, that is the optical path difference. And what was the condition for constructive interference? The constructive interference, the condition for constructive interference was delta p, the path difference, which is this one actually, and delta r, this is phase difference, because which is coming because of reflection. So now it depends upon whether the light is getting reflected at interface of when it is going from rarer to denser. In that case delta r will be pi by 2. In case it is going from, say, denser to rarer, there will be I mean it is reflecting in such a way that it is traveling from in the denser medium and gets reflected back in the denser. In that case there won't be a phase change. So suppose this is say glass. If ray is coming this way, it reflects here, so there will be a phase change of pi by 2. So delta r will be pi by 2 for this reflection. If it is glass, it is coming here and getting reflected back. So here suppose is air again, so it won't be reflected, it will be reflected, but it won't be getting that sudden path change, because now it was traveling in the denser medium and going back to the denser medium, and it was rarer one, so there won't be a phase change. So accordingly the reflection here doesn't suffer a phase change. So accordingly you have to use this one. So for constructive interference, what should be the case? That okay, this delta p and delta R should be m lambda. So now we have to see where all it has suffered the reflections. For each reflection we have to consider the phase difference to be pi by 2 or 0, depending upon what is the interface of two media where the reflection is occurring. And similarly we can obtain the condition for destructive interference. So as this has already been done, so I'm not going into details of it. What is important here is we may come across three different cases. One case is usually seen in soap films, and what happens in soap films is that, okay, I hope you would have seen the soap bubble. That is something like a soap film. So what happens is light comes from outer portion of the bubble, and then the film, which is a very thin film, and then there it suffers a refraction. Partially it is reflected back, and then inside the air bubble or soap bubble is also air, right? So this is kind of situation which we have to consider. And in that case, what will be the condition for constructive interference? This is the geometrical path difference, optical path difference, sorry. So 2 nf into t. Okay, this t is same as d. Please forgive me for this. So this is thickness actually. This t refers to thickness. So this is d in this context, into cos of theta 2. So theta 2 was angle of refraction, right? So you can say, okay, theta 2, this will be same as theta 2. So theta 2, this should be equal to m minus half lambda. This is condition for constructive interference, not destructive. Why m minus half lambda? Because here this portion suffers an additional phase change of pi by 2. This portion doesn't suffer that. So we have to take, okay, delta R to be lambda by 2 actually. So this is delta optical plus there will be a lambda by 2 here, and then this has to be equal to m lambda. So that this lambda by 2 when goes to the right hand side becomes like this. This is the condition for constructive interference in the soap film. Similarly, there is another case. Suppose we have a oil on water surface. In that case, suppose that refractive index of air is lowest, and then water is higher, and oil is highest of these. So in the same case, because now this is denser medium, optically denser means it has a higher refractive index, it is rarer one. So again here, when light suffers a reflection, there is no phase change because this medium is rarer, right? So the reflection will suffer a phase change of pi by 2 only when ray is traveling in the denser medium, sorry, is in the rarer medium, and it goes back to the rarer medium in that case. So in this case, okay, here there will be a phase change of pi by 2. So this is rarer medium, it is going back. Now here you would say, okay, this is denser, but this is denser with respect to this one. With respect to this one, the reflection happened because of these interface of these two media. So what will happen? This is denser one, so it is going from traveling in the rear and going back in the rarer one. So it won't suffer that phase change of pi by 2. So the situation is similar to this one. So rarer, denser, rarer, rarer, denser, rarer. So the condition for constructive interference remains the same. What only has been changed here are the value of this is an oil. Actually, we have to take refractive index of the film, so that is here oil film, and that would be the condition for constructive interference. This is something different one. What is usually seen in the anti-reflection coatings. So basically in anti-reflection coatings what we have is glass. Suppose your say eyeglasses, they usually have an anti-reflection coating, or even screens may have computer screens do have anti-reflection coating, some of them. So in that case what happens is the refractive index of glass is the highest. So this medium has highest refractive index, this is lower, this is lower, lowest. So what happens? Okay, this comes this way, so this is rarer medium going back to the rarer, it will suffer a phase change of pi by 2. Same here, it is rarer with respect to this one, so it comes here, reflects, so here again it suffers a phase change. Optical path difference will be the same one. I mean, this one is the optical path difference, correct? So 2 into n coating into t cos of theta 2. Now these two phase changes do cancel each other. So if this suffers a phase change of pi by 2, this also suffers a phase change of pi by 2. So both are, or both can be cancelled, and that is why the condition for constructive interference in this case will be this one. So now examiner may ask you this question in different ways. He may give you different conditions, and according to those conditions you can obtain the condition for constructive interference in the thin films. This stuff can be found in details on Wikipedia. I found these figures were very helpful, so I have taken them from Wikipedia. You can go and see details there. Okay, then was this uh, fringes of equal inclination. This is something very interesting, and what we call the Hedinger fringes. Now, this is also actually nothing but the interference from a thin film, and the difference here is that the source, which we in earlier cases were taking to be a point source, here it is an extended source. Extended source means a large size source. So it can be seen to be like, okay, made up of the source can be considered to be made up of multiple tiny point sources. So this is called an extended source. So suppose this is an extended source, large size source rather, and suppose these S1, S2, S3 are small tiny sources, or we would say point sources on the whole extended source. So what is the meaning of fringes of those equal inclination? That is what we are going to discuss. So if we take this, then the light coming from, say, this source, so it would be like, okay, the waveform will be like a say plane wave, suppose. Then the light coming or being incident from this source and this source, they are not coherent with each other. So there is no, it is not necessary that different parts of the same source may have a phase coherence. I hope you remember that, in which we have discussed in the previous classes, that okay, the two portions of the same light source, which is finite size source, may not have a very well defined phase relation, so they are not coherent one. S1, S2, S3 are not coherent one. But okay, as far as we are seeing S1, light going from S1, they are being in say incident or at some specific angle of inclination. That is why this term called inclination comes here. Important thing to notice here is that light coming from all these sources falling on the film has equal inclination, correct? So light coming from all these sources have equal inclination, and the fringes which is formed because of these different sub sources, we would say S1, S2, they would be like, okay, this will be leading to some interference pattern, and then there will be a constructive interference. These rays will be parallel to each other and traveling like this, right? Then same case here and same case here. Now these rays won't be leading to an interference, you should say. Why? Because those are traveling parallel to each other, there is no point or no reason of for those rays to actually coexist in same region of the space and lead to the superposition or interference. Now to see those fringes of equal inclination, what we have to actually do is we have to use some mechanism like a lens. So the moment we put lens, what does lens do? This try to uh, 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 collect light in at a single point. So what will happen? The light which is actually parallel to each other, light rays which are parallel to each other, they will be forced to come closer and closer and closer, and what you would see is at some point they would be interfering with each other and superposing, and hence you may find out the set of maxima and minima on the screen. And those kind of fringes are called fringes of equal inclination, because they are resulting from this kind of situation. The inclination is same, and that those fringes are also called Hedinger fringes. Next is this is another very interesting topic, and we are going to use it in detail in our next unit as well on interferometry. Um, Interference because of thin film, which is not now of a constant thickness but is having a variable thickness. So in this case, the thickness of the film was fixed, constant. Now what we want to discuss is the situation when the thickness is not constant but it is varying. So we come across many situations in practical life like this. So we first need to understand what happens. So the details have been worked out on this website, so you may go there and try to see the details, and they have also have been worked out in that NPTEL lecture, so I won't be doing the details. But okay, main thing which we had obtained or which was to be obtained in this context was, say, optical path difference. Say okay, the situation is okay, a light ray is coming here, this is angle of incidence, this is a perpendicular drawn onto this surface, angle of incidence is gets reflected, say R1, this is part of it being transmitted, then reflected according to laws of reflection, coming here, going away from the normal R2. So these R1 and R2 may suffer what you call interference, or they may superpose. Now, based upon what is the path difference between these two, optical path difference between these two, we may see whether there will be a constructive or destructive interference. So optical path difference between these two rays will actually be what? This will be equal to delta mu into BC plus CD. Suppose this is a medium, this part is here, this is a medium of refractive index mu. In that case, delta will be equal to mu BC plus CD. So because this is optical path difference, remember. So the light is traveling in this path, which is having a refractive index mu. So this is the optical path traveled in this region, and BM, this is the path which is traveled in this region by second ray. So the difference of these two will be the total path difference. Now since this has been traveled in air, so accordingly we will be having mu is equal to 1 here. So this is the total optical path difference. Fine. In other cases, there may be situation like, okay, this is denser medium, this is rarer medium. Then in that case, for example, in case of Newton rings, I will be showing you the setup in the next slides. There you have to accordingly replace the refractive indices, right? Anyhow, for this specific case, suppose this is glass slab, you can say like this. So in that case, delta is equal to, so this has been worked out on this web page in details. So delta will be equal to 2 mu t cos of r plus theta. Now correction for this is the optical path difference only. Then we have to consider the correction for phase change due to reflection. So what happens here now? Okay, here this ray, this is a denser medium, this ray suffers a reflection here, so there will be a sudden phase change here, which is pi by 2, and leads to a path difference of lambda by 2. Here there is another reflection, but this now is a denser medium, here is a rare medium, so it goes from denser back to denser, so there is no phase change. So there has to be one only, one time phase change, and that has to be incorporated here. This is the phase change. So this is the total effective, you could say, the effective path difference. And what will be the condition for maxima? That's the condition for maxima. You can easily obtain this, right? And condition for minima, accordingly you can obtain this will be the condition for minima. So now this is also known as wedge shaped film. So this has a wedge, this is wedge angle theta, so wedge angle theta is also appearing here, right? What is r? R is this angle of refraction, so this is something which can be obtained from Snell's law. We are not going into details of that. Now we have to consider fringes of equal thickness, which we call the Fizeau fringes. So the situation to that is arising because of such kind of wedge shaped films. So suppose we have two glass slides, suppose we take two glass slides, on one end we place a very thin tiny portion here, maybe some very thin, say human hair, very small, so that this wedge angle is very small. So this portion in itself acts like a wedge shaped film, or you can say film of varying thickness, correct? Now if you have to obtain what you call the Fizeau fringes, which are also referred to as fringes of equal thickness, what we do actually is we take a source and then we put a beam splitter here. What does this beam splitter do? It is kept at, say, angle of 45 degree with respect to this one. So what will this do? It will partially reflect the wave here, and we place the arrangement in such a way that this light is incident on this surface of the film at 90°, almost normal incident. So that this in this expression, this r goes to 0, and this theta is already, we are saying, okay, let us take it to be very small, wedge-shaped film. So we can in that case write down this condition actually, which was for constructive interference. Okay, at normal incidence, this equation will become like this. Okay, 2 nf, so mu is nothing but nf, refractive index of the film. T is a specific thickness from where the interference, the light is getting reflected. Fine, and this delta r is the sudden reflective phase change. If it has to be there or not depends upon the circumstances, which I already discussed. If it is equal to m lambda, then we will say it is a bright fringe, otherwise it is a dark fringe. So what happens at a specific thickness, if the light is coming from that, so this is now normal incidence. So what we will be observing is that there will be some thickness values where you will be seeing a maxima. You take the whole point to some other thickness which is slightly different. If you're taking monochromatic light, I assume lambda is fixed. You go to a different thickness, you may see a minima there. You go to a next thickness, you may see a maxima. You go to next thickness, you may see a minima. And that is how you can see the fringes of a specific shape, and those fringes actually refers to given thickness. So that is called Fizeau fringes or fringes of equal thickness. So accordingly, you may find out, say for example, this kind of things can be observed in say oil films on surface of water. You may have small thickness variations, and then you may find out, okay, some of the wavelengths leads to interference pattern, and because wavelength is also involved here. So maybe for one wavelength you may see maxima, right? Condition for maxima being satisfied, then you would see, okay, this film appears to be of that particular color, and then you may say, okay, what if lambda varies? So sorry, m varies. So if you take m plus 1 or m minus 1, the corresponding wavelength will not lie in the optical region. In that case, you may say, okay, the film will appear of that particular color. So one region of the film may be appearing to be in a different color, other portion of the film may be appearing in a different color, because there is a variation in the thickness. Accordingly, you see the color in the oil films on the what you call on the surface of the water. Fine. So that's okay. We shall be using all these expressions in our coming unit on interferometry. So I just wanted to give you a proper overview of this. Then is another very important experiment of Newton rings. So the experiment is done this way. It's very simple. You take a source of light, you put a collimating beam here, just a lens here. So you try to actually obtain a plane beam. Then you place a beam splitter here at a 45-degree angle. So this is partially reflecting. I mean, this will reflect the light, and there is a plano-convex lens capped here. So here it is actually normally incident on this particular surface. It is normal incident. So that condition of normal incidence is satisfied. This portion here is acting like a wedge-shaped films. But here is the situation is little changed. This is denser medium. This is suppose air. You may even put some liquid here. So by using this Newton's ring experiment, you can find out refractive index of a liquid as well. So fine, this is air, right? This is air here. So this is a wedge-shaped film. Thickness is changing with respect to this location on this. So if you observe the fringes here, what do you think you should observe? You know, Fizeau fringes, obviously. So corresponding to a particular thickness, you may see maxima. Some other thickness, you may see a minima and maxima, minima, and you know, lens is circular in shape. If you see the top view of this lens, it would be looking like a circle. So how should be the fringes? Those fringes should be circular in this, because if you see this, then there will be a full circle on which the thickness will remain fixed, constant. So here where this just touches the surface, this is optically flat surface, where the thickness here is 0, then it is increasing, and so on. So now depending upon where this condition is satisfied, okay, the situation is like this now. uh, this is your plano convex lens. So of course it would be having some radius of curvature. If we try some basic trigonometry, rather we apply the Pythagoras theorem, we can say capital R square, where R is radius of curvature. So this is Rm square plus this, you can see here. So where this t, this small Rm is the thickness of or radius of a particular bright fringe. Suppose at this thickness you obtain a particular bright fringe, so we can always measure the radius of that bright fringe or diameter of that bright fringe, and then we can obtain this Rm from there, right? And then Tm we can always measure again what is the thickness at this particular point. We can use this, you can use this triangle. So this is nothing but this portion is nothing but this is total is R, this is Tm, this portion is Tm, so this is effectively R minus Tm. So you use this triangle, this is R square plus Rm square, sorry, I mean R minus Tm whole square plus Rm square is equal to R square. That's it. So this further on simplification leads to this one. You can do this small tiny homework yourself. What you should see, this is something like, okay, so the reflected beam should be something like this. The central one should be a minima, then around this is a maxima, is a minima. Now I leave it as a question to you. Why will this central one will be a minima in this case? So you try to think yourself. Maybe at some later stage I will ask it to you, ask from you. So this is a reflective beam, and what you see in the, of course some of it will be transmitted as well. So the transmitted light will be opposite of this one. So here central one is maxima, there is a minima, there is a maxima, and so on. So this Newton's ring experiment can be used to find out many things like wavelength of light, or even you can obtain radius of curvature, or refractive index of say medium. Here it is air, so no problem, you can fill say oil here, whose liquid here, whose refractive index you want to find out, so you can accordingly find out the refractive index also. For that, okay, let us do a small analysis. Rather than taking radius, let us take the diameter, which is two times the radius. So the same equation if we write in terms of diameter, dm, this is same equation in terms of diameter. So dn here is the diameter. Now if we take another approximation that, okay, t square, this thickness is very small, this thickness is not very big, so we are applying an approximation that t square is approaching to 0, very small. So if we take square of this, we can eliminate this term, t square term, this one we can eliminate. So in that case we can find out that this on simplification leads us to this one, dn square, its diameter now for nth say first one, second one, third one. This is how you can find out diameter of nth Newton ring, which will be equal to 8 into t into r. Correct? Now we can apply this condition for maxima or minima, whatever we are looking at. So this is this one is the condition for maxima, I think. So yeah, in that case we can measure actually the diameter of nth Newton ring, and then put the value of t here. From this expression we simplify this for t. So t will be equal to n plus half lambda divided by 2 mu, right? So this has been substituted here in this expression, and then we can find out dn square is equal to 4 n plus half lambda r by mu. Correct? Now what we can do in this Newton's ring experiment is we can measure the radii of various Newton rings or diameter of various Newton rings, and suppose radius of curvature is given to you, refractive index is given to you, you can find out wavelength of the light. Or if you know the wavelength of light, you can measure the radius of curvature by some other method. You can measure the radius of curvature, and then we can find out the refractive index. I mean, any one of these three parameters can be obtained by measuring this one. So this is the way this Newton's ring experiment is very useful. Now that's all for today. Next unit will be on interferometers, and we shall be using those ideas which we discussed today. And first one will be the Michelson interferometer, and second one will be this Fabry-Perot interferometer. So in the next class we will be discussing about this. Hope I could convey something very useful to you related to interference, and those ideas are really useful. Thank you very much. If you have any questions, you can come back to me in the discussion. Thank you.